So we keep the house comfortable, we keep the air fresh, and it doesn't take a lot of energy to do it. Okay. So another aspect of it in terms of the indoor comfort, it's not just the air comfort, it's temperature comfort. Okay. So you don't want to have any cold surfaces in the building, even when you're sitting next to a window. Okay. So if you touch the wall here, the wall's probably 68, maybe 67. The window itself is about the same, the frame.
Oh, yeah.
The glass is going to be a little colder, but not so much. So if all the surface temperatures in the house are in the comfortable temperature range, you know, or the official threshold in this kind of climate zone is about 63, I think. You don't want any surface to be less than 63. But you want most of them to be more than that. So if you do that, everybody's comfortable. So one way you get those comfortable surface temperatures is to insulate the building properly. And properly means the right amount of insulation for the climate you're in. Okay. And in our climate, in a lot of California, the proper amount of insulation is going to be a 2x6 wall with 2 to 3 inches of insulation on the outside of that wall. And that works here, it works in Santa Cruz, it works in Napa, it'll work anywhere in the Bay Area, it'll work in Napa, it'll work in Sonoma. Here's what it is, it's a sheetrock on the inside, drywall, what you're looking at.
Yes.
And then in most cases, it's a 2x6 wall, 24 inches on center as opposed to the normal 16, so you get more insulation in there. Okay. And then on the outside of that, we get plywood, okay, and that's seismic stuff. And then we air seal that, so you actually, that's part of the air, reducing the infiltration on the outside. The whole house is covered in plywood, and the whole house is wrapped in air impermeable material, basically an air barrier and a water barrier. Okay. So then that's on top of the sheathing on the outside. Then there's 2 inches of rigid mineral wool that's attached to that, okay, to the sheathing.
Mineral wall.
And then there's about a 3/4 inch gap with furring strips. And then on the outside of the furring strips, we've attached, it's like, I think 6 inch, it's a cementitious siding. It's kind of like hardy siding,
Okay.
but it's something called Burrell. So it's similar to that, but it's got a much higher recycled content to it that they've actually certified. Like with hardy siding, they say, well, we have recycled content, but they don't tell you how much or how little, and
Yes.
they haven't bothered to have it tested and certified. So the Burrell is tested and certified. That's why we went with that, and it's cheaper too.
If I can ask you to request you to go over this again. So you've got drywall, gypsum board, then you've got 2x6 walls.
Yep.
And then you've got the
Plywood.
sheeting,
Yes.
and then you've got vapor barrier and water barrier.
Yes. And that's combined in one product.
But it's not Tyvek.
No, it's not Tyvek. Tyvek is not a good product for a
Right.
passive house.
Right, so Signa or something like that.
Yeah, it's, in our case, it's called
Pro
Henry's
Signa?
VP 100.
Okay.
It's a peel and stick membrane. It comes in rolls of about 100 feet
But
by
is this
4 feet.
one application? It's not vapor barrier, water barrier separate, it's one application.
It's one material, yeah.
Right, and
Yeah.
then what goes on top?
Then that's where then you have the rigid insulation on top of that,
How thick is that?
2 inches.
Okay,
And then the air gap,
right.
and then furring strips, when the air gap has furring strips
Right,
in
the
it.
air gap is created through the furring
Yes,
strips. Okay.
and then siding on top of that.
And what is the purpose of the air gap?
The air gap is to get air movement behind, on the back of the siding. So if you have air movement on both sides of the siding, it dries more evenly. So that's the first part of it. That's more suitable for wood siding, because if your wood siding is up against a material on the backside, it doesn't dry out as evenly. And the wood siding will have a tendency to, first of all, it can warp more readily, and the paint can degrade more readily. Okay, so it's kind of a durability issue. In our case also, what we want to be able to do is to have an air gap in there so we get air movement behind the siding so it can wash over the insulation as well, as part of a way to keep that a little bit drier.
So how critical is it to create that air barrier between the vapor barrier and the siding? How critical is it to create that?
It depends on your materials. If you have stucco, probably don't need it. You need a rain screen of some kind, so if you get water behind the stucco, it can weep out. But you don't need an air barrier. Stucco doesn't need air behind it. In fact, you probably, I don't know if you, I was going to say you probably don't want air behind it, but I don't know. I don't know that much about stucco.
And the sheeting should not be OSB, right?
It can be, but if you put an air and water barrier over the OSB, then OSB is fine. If you actually are using the OSB to be your airtight layer with no barrier on top of it, I wouldn't recommend that. I've seen demonstrations where OSB actually does leak air, so it's not airtight, and plywood is not either. Found that out on this house back here. Yeah. It's kind of airtight. You know, plywood's more airtight than OSB, but neither one of them's perfect. Yeah. So you typically do need some kind of barrier on top.
But one other question: if it's stucco instead of siding, what goes away, or does anything change? Except for the air gap.
The air gap, you're going to need on top of your rigid insulation, okay, sheathing, air water barrier, rigid insulation, you're going to need some kind of, the stucco people like paper behind that, and because that's traditionally the way it's done. But at the very least, you're going to need some kind of wire mesh, because the stucco has to have something to grab onto.
Right, of course.
Yeah.
Of course.
But that's
so wire mesh, scratch coat, brown coat, finish coat,
yes.
and all that is okay.
Yes. Yeah.
Okay.
I don't know too many people that do that. I've only been involved in one project where they've done that, and it seems like it worked fine. But we had a hard time finding construction details that actually showed how to do that from a stucco manufacturer. The stucco folks are nervous about saying, well, you can put our stucco on top of rigid insulation. They don't normally say that.
Right, and I know this might be a crazy question, but the vapor barrier goes on top of the sheeting, or it goes on top of the insulation board?
On top of the sheeting.
On top of the sheeting.
Yeah.
So before the insulation.
If you put it on top of the insulation, you have a very difficult time sealing it and making it a good membrane.
So it goes first and then the insulation board.
Yeah. No, that it addresses all of that, assuming that you have a good air barrier, and good airtight barrier, and a good water barrier.
Right.
But and this comes back to the surface temperatures also and the thermal bridging. But the way you get mold and mildew is you have moisture source, and the insides of houses are great moisture sources, and that moisture will migrate into a wall assembly, and at some location in that wall assembly it's going to hit a colder temperature. Okay, and that's where you get condensation and mold and mildew. So you want to make sure that there's no colder temperature within the building or the wall assembly where that can happen. And you do that two different ways. One is to make sure that you've got well-insulated building assemblies and well-insulated glass. Okay, triple pane glass typically, it doesn't have to be. But then you also want to have exterior insulation where you can. That's why the 2 inches are rigid, because that moves the cold spot from the middle of the wall or the sheathing to outside. So if you do get condensation, it's going to be in the insulation layer, and the insulation layer should be vapor and water permeable so that it will either escape to the outside or drop down through the insulation and escape at the bottom.
Yeah. Is that the meaning of, because James has often mentioned this phrase, airtight, vapor open?
Yes.
Okay,
exactly.
So this is what, so if there is any infiltration, the house has an opportunity, there is a mechanism for the vapor the moisture to exit.
Yes, a key component
You're
is
getting it, right?
you want all of your assemblies, if possible, and it's not always possible, you want all of your assemblies to be vapor open, so whatever source of moisture there is, whether it's from outside or inside, it can go either way. If it migrates into the assembly, you want it to have a way to get out again.
And what is it in this design that makes it go out? The vapor barrier.
The choice of the material.
The choice of the vapor barrier.
Yeah.
Got it.
You want a vapor barrier, a water barrier, and these terms are kind of used interchangeably.
Right.
You want a vapor, water, air barrier material that is vapor permeable. Okay.
And Tyvek is not.
Tyvek is not. Tyvek is a low well, I don't know about the permeability on Tyvek.
Good.
What I know about Tyvek is it's not a very durable material.
Good.
It's easy to damage it. It's difficult to detail it properly so that it'll function in all those capacities correctly. So there's materials designed specifically as air and water barriers, and Tyvek is not one of them.
And what was, forgive me, what was the name of the one that you used here?
Henry's VP 100.
Henry's VP 100.
Yeah, and on this one back here, we used to. That's a peel and stick. It comes in 100 foot by 4 foot sheets, I think, or rolls. On this one back here, we used a liquid applied material called Prosecco, and it's basically like really thick paint. You roll it on. Okay, and I did that one myself, and it's great. Anybody can build a building and protect it with Prosecco. It's a do-it-yourselfer kind of product.
Interesting.
The Henry's is a little trickier. It kind of requires some coordination, between. It's a two-person kind of thing because you have this big roll and you roll it out and you've got to get it lined up and you have to get it smooth and so that requires a little more practice.
Okay.
I think do-it-yourselfers could do it, but for this building we actually hired a general contractor, and so I didn't do it. I just watched and criticized and inspected and all that. Yeah.
So I've heard of Signa and Prosecco.
Mm-hmm.
So these are two alternatives.
Signa, S-I-G-N-A.
I think that's the
I know of some tapes
pros.
that have a name like Sigma.
Okay.
Okay, but I don't know of a
Okay.
air water barrier.
Got it.
But there might be.
Yeah.
There's so many products out there now that do this. I'm not
Yeah.
keeping track.
Okay.
It's too much work.
Yeah.
A lot of roofing material manufacturers now make air and water barrier products too. So I know there are others. Back east, there's one called Viscon that they use. That's a spray-on liquid material. There's something called EcoSeal from Knauf that I know a few people out here have tried with modest success. There's one they use back east again called Store Gold. I know you can get it here, but I've never seen a project that uses it. The only projects I've seen out here, they're passive house projects that I've actually know what they did. It's either been Prosecco or Henry's VP 100.
Got it.
And these were builders who I understand this stuff and I respect their judgment, so I just kind of acquired their knowledge and used it.
Right.
Okay, as opposed to researching the market.
Right.
Too much work.
Right.
Yeah. So the other thing you do in terms of the surfaces is you have to identify what are called thermal bridges. Okay, and this is any location in the building, and there can be many, where you actually have some kind of assembly that will promote a cold spot. Okay, and it could be things like, let's say, right here, there's a Simpson strong wall, they call it, which is a seismic structural wall.
Mm-hmm.
They used to make them out of steel, so there'd be like this big steel panel.
Right. Yeah.
This one's made out of OSB. It's like 4.5 inch thick
Right.
OSB. That's their latest version, and that's because we have a lot of windows here, and this is
Right.
structurally
Of course.
questionable. That's a sort of a big example of a thermal bridge.
Yes.
Unless if you have that kind of metal in an assembly, what you want to do is you want to put enough insulation on both sides of it so that you pretty much mitigate the thermal transfer properties of that steel plate, okay? So that the inside of the surface is not going to be colder where the plate is, the outside of the surface is not going to be colder, so that it's more likely to generate condensation or mold or moisture or mildew, those kinds of things. That's a radical example. Like, let me think of a good example. In this house, nails by themselves are not an issue. It could be if let's say you have any kind of metal penetration that goes from inside to outside.
Sure.
You can't help it with plumbing. You're going to get a little thermal bridge there, but that's acceptable. It's cases like more commonly like structural elements. Let's say in the corners. If this corner is a structural corner, we've got a 6x6 wooden beam there,
Mm-hmm.
okay, as opposed to a 2x6 wall with insulation. A 6x6 beam, wood is not a very good insulator, okay? It's not, it's better than metal, but if you have a whole corner of your building with wood, and you have, let's say, 1 inch of insulation on the outside, you're gonna have there's a likelihood that the heat in the building during the winter is going to be able to transfer through that wood and get outside. So you lose heat. And a consequence of that is you also have a colder spot here.
Got it.
Okay, so you need to look at all of the elements of the building and determine if you've got issues of that sort where you're going to have higher than desired thermal transfer through an assembly or through a location or a point or even a piece of a wall, whatever. And you want to mitigate those as best you can. Ideally, a passive house is what they call thermal bridge free. The likelihood of actually designing and building a thermal bridge free building is pretty low. So what you do is you design and build it to minimize the thermal bridges. And if you do that up to a point, and there are specific thresholds and types of analysis you do for these, and numbers involved in physics and software and modeling and calculations and everything. It can be very complicated, or it can be not so complicated depending on how you design it. But what you want to do is minimize those things as much as possible. And they typically happen at intersections, okay, corners where walls meet roof structures or where walls meet floor structures, or let's say you have a structural post embedded in one of these walls here, and it comes down and it hits this slab, and this is, there's two slabs here, but the total thickness is about 12 inches. But maybe because there's a significant structural element there vertically, we had to put actually even more concrete below it, okay? So in the case where you have a big hunk of concrete that's uninsulated, that can be a thermal bridge, okay?
What about copper penetrations for plumbing? That would not be.
You want to minimize those, and you want to minimize plumbing vent stacks going up through the roof. That's a thermal bridge also. I know it's an odd one, but it is. So overall you want to minimize penetrations of any sort in the building, okay? You should be able to, in a normal house, you should be able to limit it to incoming cold water, maybe a sprinkler connection, one or two plumbing vents up through the ceiling, a couple of, if it's on a slab, a couple of penetrations for wastewater and sewer, sewer escape from the building down this way, maybe a hose bib for the garden in the back. But we're talking, I think here we've got, you'll have two for your ventilation equipment. So I think here our total number of building penetrations through the wall is, we've got 3 in that corner, we've got 2 on the roof, we've got 2 over here, we've got 1 where the sprinklers come in, 1 where the cold water comes in, 1 for each of the bathrooms, there's 2 bathrooms, 1 for the kitchen, so that's what, maybe 10 or 12.
Right.
If you look at the way the houses are normally built, if you just look at the roof, the way they normally do the plumbing in houses, you're going to have every place you've got a water fixture, they're going to put a separate vent stack up. I'll look at a 1,000 square foot house and I'll see 6 penetrations just through the roof alone. Okay, definite source of heat loss. Okay, because that's a thermal bridge. So you mitigate that as best you can by minimizing them. And so for our plumber here, I had to say, okay, we want the fewest number of holes from the roof or going up into the roof. And so we talked about tying the vents from this bathroom over into the vents into the kitchen and combining them into one escape. And then over here in this bathroom, it was a little too far, so we did a separate vent stack over here. Okay. So any place where you have a highly conductive material relative to a good wall assembly, you have a potential thermal bridge.
Right.
One reason passive houses cost more is because they have to be designed in great detail, more so than just the design detail you need to get a permit.
Right, of course.
Yeah,
of course.
I did the permit documents and drawings for this building. It was like 3 pages, and it had no detail in it all. Nothing about the thermal bridges. It just said, okay, 2x6 wall, 6-inch SIP roof. Here's where the bathroom is. We're going to put in, as little as possible, absolutely as little as possible. And if I wanted to get that actually certified, I would have had to make a lot more detail in the drawings. Because by the time you break ground, you want to know where all the thermal bridges are. And again, this isn't a perfect world. You wanna know where all the thermal bridges are and how you're gonna mitigate them. And you wanna know exactly where your air barrier is and how you're going to put that in place and what the materials are and how you tie them together, let's say from under the slab, the connection between the slab and the wall and the wall and the roof and
Right,
everything
right,
else. You know,
So Steve, you started off by saying there are 5 elements to a passive home, and you said energy efficiency, you said air tightness.
Air tightness, and they kind of tie it, if the more air tightness promotes energy efficiency,
Right,
so they're related. Comfort and hygiene,
is the third one.
which is indoor air temperature, okay, and surface temperatures, and lack of mold and mildew and moisture and condensation, okay? So that's a goal. Those are facilitated also by the air tightness, okay, and the energy efficiency. So if you have warmer temperatures inside, comfortable temperatures inside, you reduce the risk of unhygienic conditions, okay? So that's a third leg on the table.
Comfort and
Comfort and hygiene.
hygiene, okay.
Okay. The fourth thing is continuous ventilation. Okay, and this is a California code requirement, but we're talking about better than what California requires. More ventilation, better filtration, balanced ventilation, okay? Because you want, as you remove air from the house, you exhaust stale air, you want to replace it with fresh air, and you want that fresh air, you want to know where it's coming from. You don't just want to assume that the building leaks and it's going to come in through the cracks and the holes, okay? So you get a balanced ventilation system and you run it all the time. And doing that also reduces the energy consumption and improves the comfort and the hygiene. So these things are all intertwined.
Intertwined,
Yeah,
absolutely.
okay.
And the fifth is?
The ventilation equipment recaptures heat.
Okay.
Right? Were you here when we talked about that? Okay. The outgoing air is going to be the indoor temperature, which is typically about 68 to 72. And the incoming air in the winter is going to be colder. Okay, let's say today it's going to be 58 or 60. These two air streams, the incoming one and the outgoing one, pass each other in this equipment. And as they do that, the heat from the outgoing air is recaptured and injected into the incoming air. So the incoming air that starts at 60 degrees outside, by the time it gets into the house, is going to be close to 70. So it requires no energy to heat that air. You just it requires a little energy because there's a little fan running. But essentially, it's almost like it's a free heating source, or close to a free heating source. Okay, so there you get your fresh air that increases the comfort and reduces the hygienic conditions, and it also consumes very little energy. So again, they're all like this. The fifth thing is you want to get good quality windows for a couple of reasons. One is it keeps the internal surface temperatures of the windows is going to be in that range that you want. Okay. So that improves the comfort conditions in the house, but they have a high R value, so it minimizes the amount of heat energy that can escape from the house through the windows. The windows are the weakest part of a house, absolutely. So you want to minimize the amount of heat they can release out to the outside. So the better quality windows do that. They deal with the comfort issue, but the other thing they do is you want to design your window scheme, and this relates to what you do. You want to get a significant amount of solar heat gain through the windows just from the sun. And you want to place your windows and size your windows and orient your windows to maximize your solar heat gain, because it's free energy. It's free heating energy. But you only want to do that, you want to just get the right amount. You don't want too much, because you don't want to overheat the building. So there's a whole process whereby when you design your building, you look at the window layout and the window characteristics, and you get that proper balance between just the right amount of solar gain, just minimize the amount of heat loss through the windows because of the quality of the windows, and make sure that you've got, in your case, daylighting too. You want daylighting because people like daylighting. As we designed this, our architect wanted to put clerestories like everywhere. We're like, oh my God, now that's too many windows, and it's going to be expensive, and it's going to lose too much heat and everything else. And so we reduced them to a certain extent. But the clerestories were a great idea because the natural light in this building is really pretty nice. We really like it. the master bathroom, which is right behind you, Alex, has the least amount of natural light. It has no natural light in it. Although we're grabbing a little bit from over the door that goes to the clerestory in the closet area.
It's cool, there's a transom cut in the wall.
Yeah, specifically to get some light in. Yeah, that's why we put it there. Yeah. So let's see. So we talked about air infiltration, energy consumption, comfort, hygiene, proper window selection, and solar management. Okay, to support all of these other goals. And I'm either missing one or I combined with the first
Ventilation,
one.
you said. Ventilation.
Ventilation, yes, thank you, yeah. So those are like the 5 legs of the stool. Stools don't have 5 legs,
Right,
but
right,
you
right.
know, it's a weak analogy.
Yes.
What do you do about like in the summer when it gets really hot and you already have internal heat gains from, you know, like kitchens, equipment, appliances, people.
Good questions, yeah.
Right, and
Yeah.
so, you know, in the summer it's gonna be hotter and you have the sun coming in. I see that you have shades, but
Yes.
what do you do about like cooling?
We don't have any cooling requirements because the other thing you do, this goes back to the windows and the solar aspect of it. You design it so that during the summer, you want your heat gains in the winter. And you design it such that you've got tuned overhangs so that in the summer it blocks as much of that solar gain as you need to block. So our overhangs are tuned so that on July or June 20th, we get no solar gains through any of the windows, except when the sun rises, you know, it rises over here, so we get a little sun coming through that little patch of blue there, and then it hits that tree, and then we get a little sun through that patch of blue, and then it hits this big tall redwood. That's the only eastern sun we get, so it lasts for about 45 minutes in June. On the west side, we have the same thing, okay? We only have a couple of windows there, and we get about 45 minutes of heat gain through the west-facing windows on June 20th. The rest of the year, we get nothing through here, we get nothing, well, we get a little bit through there, none of the other windows. So you manage it that way, as best you can. And we have solar shades, but those are on the inside.